Hi, good night, everyone. Welcome to the 36th PyData meetup. So today we have Mr. Kevin Baboolal, who will be talking about the GPU acceleration of the kappa algorithm, specifically for regression problems. So really exciting stuff. So Kevin, he's an experienced data scientist professional with a multidisciplinary background. Uh, he started off with engineering um, in the University of Waterloo, and then did MC Data Science, worked with Prof. Hosein. Also has an MBA in Business Strategy from Arthur Lockjack, and he tends to blend technical and business acumen that allows him to implement machine learning and AI solutions across various industries such as manufacturing, banking, and insurance, etc. So he's also currently an MPhil student upgraded to his PhD at the University of West Indies, St. Augustine. Research interests include information representation, deep learning, language processing, and accelerated computing. All right, so before we start, I'd just like to remind everybody about the community's code of conduct. Please be kind to others. Do not insult or put down others. You have to behave professionally and remember that harassment, sexist, racist, or exclusionary jokes are not appropriate for PyData. All communication should be appropriate for professional audience, including people of many different backgrounds. Sexual language is not appropriate. PyData is dedicated to providing a harassment-free community for everyone, regardless of gender, sexual orientation, gender identity, expression, disability, physical appearance, body size, race, or religion. We do not tolerate harassment of community members in any form. So thank you for helping us making this a very welcoming and friendly community for all. And Kevin, when you're ready, you can take it away.
Yep. Thanks for the introduction, Chris. And yeah, excited to present today. Hope it'll be exciting for everyone as well. My screen is sharing, yeah.
Yeah, yeah.
Yeah.
Okay, great. Yeah. So this talk, revolves around the kappa algorithm that was invented um in TTLab, and we discuss how we move it to the GPU to overcome some of the challenges. Yeah, quick table of contents. So we'll talk about the kappa algorithm, the different parts, some of the work done in terms of finding kappa, and then why it's important to move the workload to the GPU. So yeah, what was in this for you? I guess if you've never heard of the kappa algorithm, you'll hear a bit about it now, some of the applications of it, what we've done to optimize it on the CPU and where those limitations um, come into play and how GPUs are able to overcome it. So in 2021, the kappa algorithm was introduced by Dr. Hosein. He did it in the insurance domain to control the trade-off between personalization and bias. So this bias variance trade-off is what gives the kappa algorithm its strength, and that you're able to control that quite well using the tuning parameter kappa. One note, there is another algorithm from some time ago called the kappa algorithm. So we are starting to call the kappa algorithm the kappa new algorithm. Just been a bit difficult to introduce the terminology because when referencing all the uh, previous work we've done on this, yeah, it could get a bit confusing. Anyway, the core of the algorithm is this sort of weighted kernel here, and it has two steps. The first step here is equation one, where we encode a feature using a weighted average of the target value, and then we perform a prediction using those encoded features and as a weighted average of the target value. So we you kind of refer to the first part as the encoder and the second part as the regressor. So if we look a bit around the encoder, this was the equation you see before, and the main difference with this and something like KNN is that KNN is a nearest neighbors algorithm, and you just look at your K nearest neighbors and create an average there. Um, whereas the kappa algorithm uses this kind of kernel function is a way to decay that we'll see here, that controls the contribution of sample points near it. So as kappa increases, you'll see how the decay changes, and then the contribution of it is different. So at kappa equals 0 is just a straight average. As kappa increases, only the narrow points would contribute to your estimation or your encoding. Also, feel free to stop the axiom. Sorry, the animation not here because I couldn't find the file for it, and then Overleaf was being a bit weird when I was trying to take out the slides, so that's that. Anyway, this is what the encoding does. So if we look at the raw data, so X is a normal distribution and Y is from a Poisson distribution. After we encode it using the kappa encoder, you'll see that the X is now redistributed to be a bit similar to the Y, or to follow the Poisson distribution. And effectively what we're doing there is we're projecting it into a space that is similar to the target space. A kind of rough way or very naive way of thinking about it is like in physics when you would have to, or I guess any science, where you'd have to convert to the same units before you could actually do a calculation. You could think of this encoding step as taking your features and putting it all into the target space, which is the space we're trying to estimate. To show how well this encoding works, we take some data and then we perform our encoding versus different types like PCA, min, max, raw. And then we use mean absolute error to see how we get the best estimations, and generally kappa encoding works best for the encoding step. Only one case where it didn't perform as well. Similarly here, one other case. Oh, actually, this is a repeat of iris. Yeah, so only one case where it doesn't repeat. I'm kind of going to go through these things fairly quickly because we want to get to the accelerated computing stuff. Yeah, these are just some more results that show that by regressor, the kappa algorithm also doesn't have any preference. It still just does better overall. So that was the encoder, and now the second part of it is the regressor. So encoder is this first part here, and then regressor is the weighted average of the encoded values. So if we look at the graph on the left, we could see similarly to what was described before, when kappa equals 0, no personalization, is just a flat line. And as you start to tune kappa, you start to change that bias variance trade-off, and you could see the optimal value in this case is kappa equal 1.6, and that's the orange line, and that minimizes your MSC. So as you create that trade-off between bias and variance, you're basically trying to minimize your MSC to find the optimal value. Often enough that as you increase kappa, you might see a curve looking like this, kind of like the Nike tick. So you get some notion of there's a minimum MSC. It isn't always this pretty, but often enough it does follow this shape. On the left, we have a table showing how kappa regressor compares to very popular regression techniques like random forest, decision tree, and generally we have the lowest MAE here, indicating that the kappa algorithm could, hold its own against powerful algorithms like XGBoost. So kind of following up on this idea of tuning kappa, you kind of have to do a linear search, right? If you want to find what's the one that minimizes your MSE. And just to give an idea of how this behaves, so if we take like a Gaussian distribution and we try to find the optimal kappa, we could see as we vary amplitude, the optimal kappa increases, which makes sense. As we increase the noise, the optimal kappa decreases, and because the data set very noisy, want a lower kappa. And as you increase the number of points, the kappa goes up because the density or the packing of information and there's a lot higher. So you don't need to have a lower kappa that would give you a wider average over everything. So it's sort of like this this optimization of, where is the best point to average over the surface for the data you have or for the density you have. Similarly, as we vary the standard deviation of the Gaussian distribution, you'll see the kappa value goes down, and that's because there's no spread out now, right? So, the optimal kappa has some idea of, how the noise changes the amplitude, the density or number of samples, and the variance. If I use some time series information like sine, you'll see similar trends in terms of the graph, with noise and whatnot. Right. So the big challenge with this algorithm, so it has good results, and hopefully those slides have kind of assured you of that, is that the complexity is in n squared. So if you have to calculate the distances, and then you have to do the weights for each, and then like say we have a set of prediction and n train by f features. Usually the number of features is much less than your training sample, so generally is an n squared, which is not good. Oh, I mean, it's not bad, but is okay. Just as a reminder, the algorithm is in two parts: is kappa encoder and kappa regressor, and both of them use this kernel that will hit this n squared problem. So the task here now really is how do we optimize this kernel that we use in kappa to encode all the information. Okay, this is basically I repeated the slide before. Just a bit different. A single prediction. Yeah, same thing there. Okay, so this is for a single prediction. Like you already know kappa here is an n squared. If you need to search for kappa, then you kind of need to multiply by a search space in a sense, right? If you're doing like a linear search. And there's been some work done on, some of my references messed up here, but some work done on doing a successive quadratic approximation on modified golden section search to find the optimal kappa. The problem here though is your search space generally in this algorithm is much lower than this n squared complexity. So while this does help speed up the algorithm, is a much smaller speed up than you get from speeding up this computation here. And that's why we're interested in seeing how we could speed that up. So we'll start with looking at a CPU optimization, and then we'll look at what we did on the GPU. Yeah, so the first thing we did was to parallelize the operations as much as we could, and we used some just-in-time compilation. So we use number for that, and that basically reduces the Python interpreter overhead because it compiles it and then kind of moves it down closer to the performance you would see. I also use the jet decorator, which would reorder some of the operations. It does come at a small cost and precision, but it wasn't anything significant in this case. And the other big optimization on the CPU was using multi-core. Number has a neat way of doing that with p-range. So basically, if you have a for loop, you could kind of spread it across the cores. And for encoding the features, we could do this across the columns. We could also do it for multiple samples if we wanted to. Yeah, so it's single instruction, multiple data operations, and number. Yeah, does that out of the box for you. I mean, most processors, CPU processors these days have this. The limit really comes in the core count. Just to give an idea what that speed up does, parallelizer and using multiple cores, using JIT compilation. Green is like a fairly basic implementation of the algorithm using for loops, and orange is the optimized run. You can't really see it there, so just multiply by 100 and you could see like, so this is like 100 times faster than what you would see there. So it is much faster on the CPU doing this. But was the main limitations here? So you only have so many cores on a CPU. compared to like a GPU. So you have some saturation there, and then the inner loop technically is not fully parallelized because you could end up with a sort of race condition if you parallelize the prediction of all the test values and then try to parallelize across the train values, which is something we could get around on the GPU. Another big drawback is the memory bottleneck. Just to give you an idea of what that would look like, if we had, 1,000 test samples, 5,000 train samples, and 100 features, which is a lot, and 64-bit precision, generally the biggest array when you have it all, because the speed up coming at the cost of memory, right? Is the differences. So when you calculate the differences in all the distances, and that could quickly end up being an array that's 4 gigabytes, which is quite sizable. It's a temporary spike in your memory use, but still quite sizable, and does become a bottleneck on your CPU. Okay, we're gonna look a bit at the GPU optimization now. So on the GPU, we do 2 levels of parallelism, which is intersample. So we're gonna predict each sample on each test sample on I guess I should say each test value on a different block. And then we're gonna compute the distances and the weighted sum, the distances across the threads, and then we're gonna use some shared memory for the weighted sum, which hopefully will be a bit clearer in the next diagram. Some key things we do, so we use strided memory access. And this, basically we're trying to coalesce the memory, and this gives us significant speed up on the GPU. You can think of it as like within each instruction cycle, we optimizing the number of reads of memory we do. And to do that, we had to transpose the data as well to kind of fit the architecture of the GPU better. And then we also use the shared memory, which allow for much faster read writes across the threads. So to kind of make that a little easier to understand, we have a diagram here, which inspired by Chris. But yeah, so if you have, this is your testing values. So you have, m different values you want to test. Each one will go to a different block. And then you have your features computing here, and then x1, x2, x down to n is your train values, and you compute them. If p threads, you'll be computing on p threads at a time. If we step forward in time 1, you'll see we compute this row, and then we're gonna continue computing the rows. And each time you finish a row, you have the shared memory on top within each block where you store your numerator and denominator of the weighted averages there. And then once a cycle is completed, we will sum across this memory location and get our prediction. So that's the only parts where like you have some synchronization happening, and that does lead to a bit of a bottleneck, and we'll see what that kind of looks like in a bit. Okay, so what do we do to the complexity there then? Really and truly, the complexity remains the same, but now we scale it by the number of blocks and the number of threads. So if we look at, so in training, let's say that the training set and the test set is equal to n, and f is the number of features, as we were saying before. You would get, it's still n squared, but now scaled by this parameter here. If we take the CPU time and divide it by the GPU time, then we get, that scaling factor of BP. And to, I guess, make that tangible, on our RTX 6000 GPU, we have 84 blocks and 1024 threads. So the max speed up we would expect to see in that case is something like around 86,000. So some results. The GPU times on a small data set, you'll see like the CPU time is, able to compete with the GPU. And that's kind of expected, right? Because you don't have the overhead of moving the data into the GPU. But as you get to bigger data sets like Pokahan, which is 1 million values, you'll see the CPU will take 55 seconds and the GPU will still take like, was that 9.9 milliseconds? So yeah, it scales really well, and even for small data sets, it's still pretty much comparable. Not much change in the accuracy. Not too sure why this one had changed much. But yeah, there's no significant difference in the MSCs really, at least to this precision. And then, so the max speed up we'd expect to see is 86,000. Now, what we did here was we basically created a synthetic data set and run it on the CPU versus the GPU to see, what was the max speed up we would see before it started breaking down. And around like 850,000 rows, we saw a speed up of like, I think this was 58, close to 58,000. And then it started to go down after that. And that's kind of expected because and so you have like some overhead with launching the kernels. You do have the CUDA synchronized, which could cause some bottlenecks. And just overall like scheduling issues. So we do expect to get the theoretical maximum because the equation doesn't account for all those um, intricacies. In terms of this one dropping down here, yeah, I think it's a bit of an anomaly where the CPU and GPU take like around the same time. Yeah, not too sure what was happening on the machine there. So this is generally with the CUDA architecture. I have done it on MLX as well, which is Apple Silicon. I didn't have enough time to put it in the slides here, but it does show a similar improvement. And it's an interesting test because the Apple architecture is the unified memory. But yeah, it does show similar improvement. Though Apple a bit more vague with how much cores it actually has in the GPU and the logical units. So thank you for that. Hope it was interesting. Yeah, any questions, thoughts?